Mr. Gibson here. Today we're going to look at another specific type of sequence called a geometric sequence. In our first lesson, we kind of got an introduction to sequences and series. In our second lesson, we looked at a particular type of sequence called an arithmetic. And if you recall, the arithmetic sequence is created by adding or subtracting the same amount each time. We called that the common difference. And then we looked at the recursive and explicit formula for arithmetic sequence. So we're going to do a similar thing today for what we call a geometric sequence. So let's look at our objectives here. The first is, how do we know or identify that we're working with a geometric sequence? The second is, how do we generate geometric sequences using the recursive or explicit formula? And then the third is to use, in this case, a geometric mean to find a missing term, similar to what we did with arithmetic sequences. We use the arithmetic mean. So geometric mean a little bit different. All right. So let's start with a definition. In a geometric sequence, the ratio between consecutive terms is constant. Now the key here is ratio, right? So let's highlight that. Put my highlighter on. So the key is that the ratio between consecutive terms is constant, and we call that the common ratio. Now it can be positive or negative, but it can't be zero. So let's look at an example and see, where does this common ratio come from? So here's a sequence, 1, 3, 9, 27. And is it a geometric sequence? Well, to confirm that, we want to see, does each term have a common ratio compared to the term before it? So let's test that. So how do we get from 1 to 3? Now notice we find the common ratio by taking a term and dividing it by the previous term. So we're going to take 3 and divide it by 1, and we get a ratio of 3. This is really just another way of saying we're going to multiply the first term to get the second term, right? If we're working backwards, the opposite of multiplying is dividing. So that's why we take this ratio. Let's check the next one, 3 to 9. Well, we see the same thing. 9 divided by 3 gives us a common ratio of 3. And I'll do it one more time here. 27 divided by 9 gives us a common ratio of 3. So if we get the same value each time we do this, then we say, yes, it's a geometric sequence and it has a common ratio of 3, or it's another way of saying we're going to multiply by 3 each time. Okay, so if you remember, in arithmetic sequence, we were adding or subtracting a common difference. In a geometric sequence, we multiply by a common ratio. All right, let's look at another example, see if we can determine, is it a geometric sequence? 15, 30, 45, 60. So let's check it out. 30 divided by 15 gives us 2. 45 divided by 30 does not give us 2, right? We can simplify that, divide each by 15, and we get 3 halves. 45 divided by 60, same thing. We can simplify, but we do not get 2. We get a different value for thirds. So from this, we can see that we don't have a common ratio and that this would not be a geometric sequence, okay? If we look at it, we might recognize that what we're actually doing here is adding 15. So this is a arithmetic sequence, but not a geometric sequence. All right, let's try a couple more of these and have you decide, is this arithmetic, geometric, or neither? Okay, so we have 2, -4, 8, -16. So let's do the math, right? Take each term, divide it by the term before it, and see what we get. And in this case, we see we get -2 each time. So we would say, yes, this is geometric, and the common ratio is -2. All right, have you try another one here. I'll go ahead and pause the video, see if you can determine if we have a common ratio. All right, let's set it up. So in this case, we can recognize that we're not multiplying by the same amount, but we are adding, right? We kind of have to look at this a little bit first, because remember, we're asking, is it arithmetic, geometric, or neither? Okay, so we're looking for both here. But in this case, we can see that we are adding 12 each time. Now, if you started to go ahead and solve for the common ratio, you would quickly see that 20 divided by 8 is not the same as 32 divided by 20, right? We would not have gotten a common ratio. But in this case, we have a common difference. All right, let's try a few more of these. Now I'm going to give you a little different pattern here. We have bacteria and they're multiplying. All right, so let me stop there. Can you determine whether this is arithmetic, geometric, or neither? Well, what you might want to do is count the number of bacteria, right, for each of the term. We started with 1, and then 2, and then 4, and then 8. So here's our sequence. Is there a common ratio? I think we recognize, yes, we're multiplying by 2 each time. It makes sense because basically each term we double the number of bacteria. So we'd say, yes, it's geometric. Its common ratio is constant. All right, let's try a couple more. 1, 4, 9, and 16. So let's try common difference first and see. We don't get the same value, 3, 5, and 7, if we subtract the previous term from the next term. If we were to divide, right, we'd have 4 divided by 1, that's 4. 9 divided by 4, a little over 2. 16 divided by 9, not 1 or a little over 2. So in this case, the difference is not common. Let's try the common difference by dividing. And again, we see that the common ratio is not constant, okay? So what can we conclude? Well, it's neither arithmetic or geometric. So we just have to say neither. It's some other type of sequence. You might recognize, see if you can figure out the pattern, but in this case, it's not arithmetic or geometric. All right, so we know how to recognize which case we have. What do the formulas look like? Remember, we're going to use recursive and explicit throughout the rest of this unit. What do these look like for a geometric sequence? So here's what they look like. The recursive, remember, is used to find just the next term if we know the previous one. So here we're taking the previous term, right, n minus 1, and multiply it by the common ratio. And that makes sense, right? That's what we're doing on a geometric series, is just keep multiplying by the same value. And that value is r. Explicit formula looks a little different, gets a little bit more complex. It still uses the first term, and it uses n, right, for whichever term we're trying to find. But here we're going to take the first term, multiply it by the common ratio, but the common ratio is raised to a power, and that power will be n minus 1. And we'll look at an example in a minute of how to plug it in and use that formula. Okay, r is the common ratio, n is the number of terms, and A1, of course, is the first term, okay? All right, so let's look at an example. We want to find the fifth term in this sequence, 4, 12, 36, 108. So we could use either formula, but we have to figure out what the common ratio is. So take a look at that. How do we get from 4 to 12, 12 to 36, 36 to 108? Well, we're dividing by 3. Or we get 3 rather if we divide, right, the term by its previous term. So same as multiplying by 3. And we know that the fifth term n would be equal to 5. So Let's plug it into the recursive formula, right? We're trying to find the fifth term, so the fourth term would be 108 times 3 gives us 324. Notice in geometric series, or sequences, the values are going to get very large quickly, right, if we're multiplying. All right, let's try one with the explicit formula. Here we're going to plug in the first term 4. We put in our value of n, 5. Now be a little careful here when you do this on your calculator. You want to think about order of operations. So the first thing we do, right, is exponents. So we want to take 3 and raise it to the 4th power. Do that first. That gives us 81, and then multiply it by 4. So we get this, we get the same answer, 324, using either formula. All right, let's get a little practice here. We want you to find the first 5 terms and first use write the explicit formula, okay? So here, to write the formula, you have to be given, right, the first term and the common ratio, in this case, a -3. So the explicit formula, we're just going to plug in, right? The first term 5 will go in for A1, and -3, right, will be our value we'll plug in for R. So here's what it looks like. Now, there's nothing really we can do to simplify this, so we're just going to leave it in this form. A sub n equals 5 times -3 raised to the n minus 1. Now, if we wanted to generate the first 5 terms, there's a couple ways to do that. We could use the explicit formula each time, or we know we're simply going to start with 5 and then each time multiply it by -3. So we get 5 times -3 gives us -15. And then times -3 again, we get 45. Okay, so we can generate these first 5 terms probably most easily by just using the recursive formula. All right, let's have you try one more and then we'll wrap this up. Here, the first term is 2 and the common ratio is 0.1. So pause the video, see if you can write the explicit formula and generate the first 5 terms. Okay, here goes. Explicit formula. Going to plug in 2, right, as the first term, A1. And our common ratio is 0.1. We put that in for R. Now, if we were to use that, basically what it says we're going to do is multiply each term by 0.1. So that's really dividing by 10, right? So each time we multiply, we're basically just going to move the decimal point 1 to the left, okay? So we start out with 2, and then 0.2, and then 0.02, 0.002, okay? You can see what we're doing here as we multiply by 0.1. The values are going to get, in this case, smaller and smaller rather quickly. Now, the last topic in this lesson is the geometric mean. So we use this to find the missing term in a geometric sequence, okay? And we do that by taking the square root of the product of the 2 numbers, okay? So let's look at a little example of what we're doing, right? Let's say here are terms in a geometric sequence, A1, and A2 is missing, A3, A4. So we want to find this missing term here. Let's get my pen on here. So this is what we're trying to find here, right? What would be this missing term? So we're going to use the geometric mean, which would say we take the term before, right, A1 winds up here, and the term after, A3, in this example, we multiply those together and then take the square root, and then we get our value here for A2. Okay, let's look at an example and try this. So 20 and then 80, and the missing term in between is what we are trying to find. So we're going to use a geometric mean, which says we multiply 20 times 80 and take the square root. That would be 1600 take the square root of that, and we find our answer is 40. Okay, so 40 will go up here, and it makes sense, right? We can kind of test this. 20 times 2 would give us 40. 40 times 2 would give us 80. Okay, so we have a common ratio of 2 in this example. All right, I'll have you try one more, and we have 3 terms that are missing. But here's the clue here. Let's find the center term first, right? Do this first, and then see if we can find the other 2. So go ahead and pause the video, see if you can do this, and then I'll wrap things up. Okay, here we go. Middle term. 2 times 1250. Take the square root of that, we get 50. Now we can find the other 2 missing terms, right? 2 times 50, square root of that gives us 10. And then the 4th term, 50 times 1250 gives us 250 if we take the square root of that. Okay, so that's how we use the geometric mean to find missing terms in a geometric sequence. All right, so that's the lesson for today. We've learned how to identify geometric sequences, generate geometric sequences using the explicit or recursive formula, and then use the geometric mean to find a missing term. Ignore this assignment in here. I will have a worksheet posted for you that goes along with this assignment. All right, thanks.